bit of a schedule altogether. But you can also just switch it. Just switch it.
Right. 4 o'clock. Time to do some algorithms. So, welcome to algorithms, everyone. Come on, take a seat. Come on, get in there. So, algorithms is a pretty special course. It's for a couple of reasons, but I think predominantly, this is very likely going to be the most important class that all of you take at UMass. Very likely. It's a class that is helpful for every single one of you. It's a class that I've used the most in my life. In fact, I took a technical interview last week. I take another one this week. Both of them. This was the #1 thing that helped me take them. All right? So it's very useful if you want to go into industry. In my research, this was the #1 thing that saved me time. And I even wrote an algorithms paper, which obviously I needed this for. And even for those of you who want to just be a vibe coder and get on by, you still need to know the basic principles of this to write half-decent code. To even be able to talk to an LLM about what you need, what your constraints are, you need to understand this class. So, $1,000,000 question. I already broke my chalk. $1,000,000 question. What is an algorithm? Obviously, we've all heard the term, but I would like us to try to formalize it. Anyone want to give it a shout? Yeah.
A set of guidelines.
A set of rules or guidelines to complete a task. This is a reasonable answer. So this is, you can imagine, what is the difference between algorithms and just writing some code? If I wrote some code, I could do some quick and dirty script to figure out what I need to do. When I write an algorithm, then a whole class of problems are solved. If I get any combination of inputs, my algorithm will handle it one way or another. Beyond this, I'd say the major difference, there's still a major difference between writing an algorithm and just writing code. Anyone else want to give it a shout? Any ideas? Yeah. A method to get from one point to another. I think that's a little bit too general to say this an algorithm. I'd call that a function, for example. I'd say probably the biggest distinguishing factor between writing code and writing an algorithm is in analysis. So this course is going to start and is going to end with quite a bit of analysis. So we need to know how long does it take for our algorithm to run in a variety of different metrics, how much memory does it use, is it correct, when is it not correct, etc. There's a lot of analysis to do, and the majority of this class, the majority of the difficult part of this class for all of you, is going to be in the analysis. There is, of course, a certain artistry, a certain difficult intuition that comes with writing an algorithm in the first place, but the true test of this class is in doing analysis. Okay? Hopefully I've set the stage for you all. We'll get to touch on this a little bit later today, but of course it's the first class, so it's going to be mostly administrative stuff, although we are going to cover some content today, depending on how long it takes. First up, I want to ask, are there any questions? Any questions about what the class is going to be? Obviously I'll talk about this a lot, but I just want to know ahead of time. Okay, second question. Anyone want to be a volunteer? Yeah? All right, cool. Hold on to these. I'll tell you when. Okay? You can look at it. Ooh, he gets extra privileges. Okay, so the way that my class is being run, by the way, this is my first time ever teaching 311. Go on, sit down. I've taught previously machine learning. I've taught introduction to programming. Some of you have had me in probably only the introduction to programming, not the other. I also have TA'd a lot of courses, so you've probably seen me around. I'm a PhD student, in case you're curious. I'm not a professor. I'm not a faculty. It means that I do the same job and I get paid a lot less. This course, I am taking some of my own liberties with. I enjoy this course a lot. I've been pushing to teach this course for a long time because I think it's a very important class, if you didn't get that from my spiel. And I think that it is one of the most interesting classes, and one that I have TA'd quite a lot of times, and I am excited to teach. That said, I do have a particular style with this sort of thing. So one big difference between this course and the other courses is that 30% of our final grade is going to be in-class quizzes. That is, maybe you can guess what I just handed him. We'll talk about that more later, but for me, my personal pedagogy about what it means to teach and what it means to learn, I believe that as long as you all are in this classroom, you're going to learn plenty. So that's my number one concern. Secondarily, we're also only going to have 3 or 4 assignments. I actually don't have the number totally pinned down yet. These are going to be larger scale projects. It's going to be a mixture of writing algorithms, coding, and doing analysis. And there will be a place inside of that for you to use LLMs also. Notice that I said a place. LLMs have made everything really difficult, actually, as a teacher. I think if I can get through to all of you, fundamentally, why I think it's important that you don't do it, maybe you'll understand, maybe you'll listen. But I understand that quite a few people are probably going to do this, and I'm just going to design my class around negatively incentivizing that, I suppose, or not incentivizing it. So with LLMs, it's very, especially for a course like this, where a lot of the material is going to be well-tread. This is stuff that you can look up online very easily. A lot of your homeworks, a lot of your projects, a lot of the content we talk about is going to be online. It's going to be easy to find. It's going to be easy to copy and paste. Not to give you ideas. I will do my best to modify in such a way that you won't be able to do that, or that an LLM will have trouble with it. But a lot of the justification I think people use for this is either that they are very worried about their grade, which I know that probably talking about 30% being in class quizzes is scary, but trust me, every class that I've done has had about an average of an 85. I expect the same for this. I don't want you to stress about your grades particularly, but I do want to challenge you, and I do want to give you very accurate feedback on what you've done. That is both in what you did wrong and the magnitude that you did it wrong. So know that some of the assignments that you get, you'll get very low points on something if you did something wrong, if you did a substantial amount of it wrong at least. But know that that's just to give you all feedback. At the end of the day, I expect that the average will be about an 85, and if it is too low, then I'll be scaling it up to that. Okay? So don't stress too much about grades. If you're doing poorly in the class, talk to me. Cool. With LLMs also, it's easy to say, okay, in a real job, I'm going to have this LLM. I'm always going to be able to use it. And this is very much like an argument you might get from a high schooler learning calculus for the first time. I can be teaching them the basics of calculus. I can be saying, what is the derivative of x squared plus e to the x, whatever. I have to do it. It's very, very easy to pull up Wolfram Alpha and get the answer, and you'll get by in everything in that high school class. But then when you need to learn the more difficult material, as you approach the frontier of what we're actually working on, you need to have the knowledge. You need to understand the fundamentals, and that goes doubly for algorithms. This is not something where, trust me, I've worked on real algorithms projects. You can't just plug it into ChatGPT. You're not going to get a good answer. Okay? So you need to do this. So hopefully, to some degree, that is justified to you that this is something you do need to learn. We're in an era now where I've interacted with students who really do not know their material because they use LLMs too much. I don't want that to be any of you. Okay? All right. So, I guess I will add on to this. I'm not oblivious to the idea that there are LLMs, and I do want to teach you all how to use LLMs somewhat. So there will be places in your assignments that are going to be hard problems that you will be allowed to use LLMs for. But these are only going to be problems that are legitimate, real-world problems, not the stuff that you'll find in this textbook. Okay? All right. One other policy that I think is important to get off the rip. No laptops. Yeah. Put them away, put them away, put them away. No phones, too, if you can. Yeah. So unless, that's fine. Taking notes on iPad is fine.
I close my eyes if that helps.
Yeah. I will say, if you are very adamant about having a laptop, I will allow it only for the far back row. Okay? So, yeah, I know, sorry, you just put it away. But only the far back row. Justification for this, by the way, more than it being personally distracting to all of you, which so much research that it is, so much research that you learn worse if you're staring at a screen. More than that is I remember being an undergrad at UMass, and I remember sitting somewhere in the middle back, staring at someone playing video games in the front row and missing the entire lecture. Not allowing it. Okay? Work on pen and paper if you can. If you have an iPad or whatever, that's fine. Also, I'm going to be using the board for like everything. So you probably want to move up if you're having trouble. I mean, this is written very big. I'm going to write smaller than this for the actual lecture. Okay? Cool. So the rest of the points in the class, I guess I should maybe put them out here so you guys can write them down if you'd like. Syllabus is online, by the way. We're going to be using Piazza because I hate Canvas, but they make me have a Canvas. So we have a Canvas that links to the Piazza. Where everything's going to be. We're also going to be using Gradescope for grading because it is just objectively better than any other way I've seen do it. So make sure that you go on the Piazza, that you sign up for the Gradescope. I'll give you the entry code and all of that. Additionally, there's also going to be a link to a when to meet where I want you all to put your preferred time for office hours as well as the SI session, which we'll talk about in a second. Just fill that out today or tomorrow, like as soon as possible. You'll find it on the Piazza. It'll take a second. Okay. So, 30% is going to be quizzes. 20% is going to be projects. We also have a discussion period every Friday. One difference between this section and Pravini's section is we do not have the mock midterms. You may hear the other students talk about mock midterms if they're in the other section. We aren't going to have that. We're just going to have discussion problems. There's only going to be 3 exams, and that'll be all the exams that we're going to do. The idea with doing that, by the way, the reason Pravini is doing that, in case you're curious, is really to deal with the fact that sending you all home with some code means a lot of LLM slop comes back, so we're trying to limit that as much as possible. Anyway, but I'm doing it as live discussions. I prefer them personally. Anyway, 30% quizzes, 20% projects, then that's going to be 20% for the discussions. Actually, I think this is actually 30%, sorry. It's on the syllabus, Also, don't worry too much about the actual percentages. I just want to let you know at some point, but do your best in all the material. Yeah. And lastly is 20% for the exams. Yeah, it's one of they may be swapped. I made that decision a little bit ago between them. It's online, But you'll figure it out, it's fine. They're both some substantial amount of your grade. Yeah, question.
So this is like the percentage for...
Yeah, final grade, yeah.
I thought on the syllabus exams are 30%.
Sure, swap them. It's another thing for me. I would like you all to not care about these numbers as much as you can. If you want to check how you're doing your class and all of that, that's fine. But again, do all the material and try your best on all this stuff, and you will pass the class. That's like almost always that's the way that it goes. Yeah.
Class is going to be recorded.
Classes are going to be recorded. In fact, this is recorded right now. So say hello to online. I don't know exactly what I think this is the camera, and also the reason I'm wearing a mic is because of that. Yeah, classes are recorded. Cool. Discussions are going to be run by TAs and UCAs who are also going to be hosting office hours. By the way, I'm going to very strongly recommend that you go to office hours. Specifically, if you're working on projects, I mean, obviously all of you know what office hours and all of this, but I really am adamant about this, that it should be sort of your first stop if you're having trouble on the homeworks at all. I found in general that if you go to a TA, like spend the time walking from your dorm to the office hours, sit there for an hour or whatever, it will save you a lot of time in the long run. You'll spend a lot less time on the homework, you'll have a lot more confidence about the material, and almost always the students who come to every single one of my office hours get an A. That's not to say I'll give you an A for showing up, but it's very likely that you'll get it. There's one more thing in our grading scheme, which is going to be bonus stars. So this is a concept that I'm pulling back from 110. Basically, on all of the assignments, as much as I can help it, there will be bonus questions on all of them, on the in-class quizzes, on the discussions, and on the projects. And each of them will be rated on a difficulty from 1 to 3. And each one of those, if you complete it, if you get 100% on it, we're going to grade very harshly on these, by the way, then you'll get a bonus star. These bonus stars are worth 0.2% of a grade point per star. per star. Just enough that they will likely shift you up from a lower grade point if you're right on the brink, but not enough to really substantially matter, to be honest. There will be about 30 of them through the entire semester. That's roughly what I'm trying to do, and they will be very hard assignments, so they'll be very difficult. In addition to getting this little grade point boost from these, you'll also get, if you have more than 20 of them at the end of the semester, I'll write you a letter of recommendation. If you want to get a letter of recommendation from me, that's how you do it. Really annoying to have to write a lot of, so this is how I limit them. And after you have that, then you can ask me for a letter of recommendation, and I'll guarantee it to you unless there's some other reason why I can't. Furthermore, every year I take one student to be sort of my mentee that I help with either research or whatever else they want to be doing with their life. Whoever has the most stars will get preferential choice, but if there's another student who really shows that they're worth it, then I'll probably go with that. But they'll get preferential treatment if you have the most stars in the class. You'll be in the race. Yeah. Okay. I think that's all of that. Last things. So office hours are going to be on again. Fill out the ones meeting on Piazza. And we're also going to have the SI sessions. The SI, if you don't know, so Tomas here, you want to come up and say hi? Sure. So SI as the student instructor, I think is what it is, something like that. Someone who's taken the class, done well in it previously, and is going to be hosting office hours and review sessions, stuff like that. You can say any more about that I missed.
Yeah, hello, I'm Tomas. I'm a senior taking computer science and linguistics. Like you mostly described, well, what SI is, technically, it's close. It's supplemental instruction.
Then.
But pretty much, if you don't know what SI is already, I pretty much hold a review session twice a week. And it's sort of similar to discussion. We do like practice problems that and it's like in a smaller setting than a lecture. So if you like learning through practice, it's good for that. And yeah, like you mentioned, for the when to meet for the office hours will also be the when to meet for the the when to meet for the office hours will also be for the SI sessions. So I guess and some of the candidate times for the SI sessions that I'm looking at are at 7 or something. So even if you're thinking oh no way he's gonna have office hours at 7 p.m. Still fill out those times because that matters also for me figuring out what time the sessions are. And yeah, I think that's about it.
Cool. Yeah. His deadline for those numbers, by the way, is in a day or two, right?
Oh yeah, it's tomorrow night. So
tomorrow night. So fill it out easy. Fill it out tonight for him, please. It'll make life easier for him and for us because we're going to do the office hours also early this week. Okay. So with all this said, the outline of the class. Any questions about how the class is going to be run? We already have dates for the midterms, by the way. They're not on the syllabus, but I've already had them scheduled and everything, so I'll tell them to you when they become relevant. There's going to be one in March, one in April, and then the final in May. That's going to be the way that it works. So you're going to get a little break from that up until. Yeah.
For the March midterm, is it close to the spring break?
It's right before spring break. I'm not putting it after spring break. I know that always sucks. Yeah. Cool. Also, if you have disability services, if you need extra time or whatever, we're going to have a separate section for disability services. I decided to have us run it so you guys can have a TA rather than disability services. But you'll need to let me know ahead of time if that's you when the exams come up. Do you have a separate question?
Yeah. So for the stars, you only get an extra 0.2 if 100% on the challenge question, and then do you get a different amount of stars for the different?
Yes. So there'll be a variety of difficulty. You'll see an example of it today, in fact. Where some of them are easier than others. Some of them may be very easy if you've seen other material before, but the ones that are a 3-star difficulty one is going to be very difficult. These are going to be questions that I expect would be very, very difficult for you to do without the help of LLMs or internet or something like that. You need to use something like that. By the way, in terms of collaboration on the projects, I have no problem with collaborations. I do have problems with copying and pasting. So I'm going to extend an offer of trust to you all. When you work on one of these assignments, I'm fine with you working on it with someone, talking through the problem. I think it's a great way to learn, in fact. I'm positive about it. But if one of you is just solving it and then the other is copying and pasting it, that's garbage and I hate it. So please don't do that. I'll trust you all on this. If it ends up being too much of an issue, we'll have to deal with it. I guess that segues into cheating policy. Some of you may know this because you were in 250 last semester, but cheating has gotten worse at UMass. It's always been an issue. It's a thing that I guess some people. By the way, no laptops. Yeah. Yeah, we're one of those. Yeah, so, a lot of people have been cheating, and a lot of times we can tell, but a lot of times it's a little bit too annoying to deal with. I think I'm going to set a different precedent for this class. I'm going to try to deal with it. I really don't want to have to, but I think it's become important where, people are estimating that about 50% of the classes are cheating. And I'm going to go hard no on that because that's a waste of everyone's time. It really is. Particularly on exams, I know a lot of people sort of form cliques and they cheat together. On exams, there's a lot of like pressuring each other through social pressure to get someone to send you their answers. If any of that's happening, let me know and I will drop the hammer of God on them. Okay? So don't let someone pressure you. Care about your own learning. Do not cheat on the exams. If I see any of you cheating on the exams, I'm going to give you an hour-long lecture about why you shouldn't do it. I'll give you a 0 on the assignment, and I'll report you to the university. It'll suck, okay? So don't do it, please. I don't want to have to do any of that. Well, it's important to do now. By the way, I have been a student. I know the things. I know you can bring 2 phones to an exam. You can go to the bathroom and use one phone in the bathroom while leaving one here. I know about all that junk. Again, really, really don't do it, okay? Okay. All right, so, all that said, now, we've talked about the in-class quizzes. I think it's time that we give you a demonstration. So, that's you, yeah. So we have Tomas and, what's your name? Lucas. Are going to, I'll take some of them too. Have all the quizzes. I'm going to pass these around. I'm going to give you, I think, 10, maybe 15 minutes to work on it. We'll see how people are doing. Here.
Person. How do you know? Is it in person submission or grade school?
It's my last
It's going to be by the end of the day, actually, but I'll talk about this after.
You want to make some? I have brand sticks. Oh, that's went from $30 to $150.
Here.
Let's wait for now to see if it goes up more. If it doesn't, easy. How many? It's 150.
He's lying.
I was actually going to send it to you something. I was actually mid-transaction, but I got denied. I got that SSN side.
Thank you. Never use the fancy chart. Can you pass that around, everyone?
No, you can use that.
There are enough quizzes, so everyone should have one. If you don't have one in like a minute, let me know. Yes. Individual. Yeah. You still missing one?
We're missing a couple
I
of
think there's a block right there.
Awesome.
Yeah.
Never mind.
Try to grab one of these ones. Yeah, for future classes, I might leave them out or something, but I also kind of like the disorganization. All right. Yeah.
The written response to those are actual.
Yeah. So for the written response, pseudocode. All of algorithms is going to be pseudocode when we are writing out the algorithms, except for the projects where we implement them. Where I'm probably going to force you guys to use Python just so that we can have a standardized grading. Python's fine for all the stuff we're going to do. Anyone got an extra pencil or pen? Either way. You're in charge of getting it back to him, by the way. You should take the quiz too, by the way. You don't have any? Are there any extra quizzes around? Yeah? Okay. I'll come grab them. You just keep working. Those are one on the floor for that. Good gosh, individual. No laptops. Okay, so that is, so that's 10 minutes. And you may be saying to yourself now, looking at this test, was I supposed to know all of this ahead of time? This is worth 30% of my grade, and other expletive things like that. Well, here's how the quizzes are going to work. You may now talk to someone next to you. So for the next 10 minutes, you can work with any partners that you see fit, although you do need to work with someone next to you. Okay? Continue to work alone. Okay? Go. Go.
done it in like. I was thinking I had to use it like Java. I don't think there's really I suck up. The whole time was like, so I think that makes it a lot easier. The two lists you're given the team to be good, and I didn't like that. It's a little different. I don't think it's like because you can have 1 and 2 in one list, and then the next
This thing minus me. I was ready minus me. It's the left one and then this one. I think this
I guess we would check the hour count of its feature.
I could do it.
I'll have an error. Yeah. It would be like, let's say my notation.
You have to be save that it's
I would say like I and J like the same like
I see what you mean.
no like either doesn't yet. Then you just push the small
Like one from there's a repeat.
and then at the end for the number like less than 50 is like
Oh, like we have to ask you.
Say count.
Like I have to use
everyone. So I was thinking here's one to basically just gives this and then you'll just push the rest of the elements. So
I mean, do you know how to have it works for one step and then we assume
Alright, so hearing it quiet down is usually my cue to jump in here. So, now what we're going to do is we're going to go through the quiz. And here's pulling back the curtain, here's why I'm doing this. I find that my favorite way to learn this material, to learn any material, is to first try it myself, leave it as a difficult open problem, and then learn the solution, and then I can appreciate the cleverness. So, these quizzes are difficult, and they'll cover material that you generally will not have seen. Maybe some of you will have seen it before. That's fine, because these quizzes are entirely graded on completion. So, congratulations. You don't need to stress about them. Okay? That's the idea behind them. I find that it works very well. I like being able to explain a solution to someone else is also a very powerful way to learn. So hopefully for all of you, this was maybe a stressful introduction to this setup, but this is the way we're going to do it going forward. The only thing where you're not going to be able to work with anyone or you're going to be really time stressed on all of this is going to be the tests. Besides that, everything else is, this should be free points for all of you. By the way, in case you haven't read the syllabus, 2 of them get dropped, by the way. So I'm going to allow you to miss 2 classes. I'm going to say that there are some classes that if you miss are going to really suck to miss. They're going to be really hard to make up. So if you are planning on skipping one of my classes, I guess maybe ask ahead of time which one's a good one. But the general answer is probably going to be none of them. But if you're sick or something like that, everyone gets 2 freebies. And then if you have to be absent for some other reason, there's a form on Piazza to fill out. By the way, these quizzes are not going to be every lecture, but they're also not going to be every week. They're going to be random. Maybe I'll even actually flip a coin to see when they are. I don't want people to say, oh, today's not a quiz day, it's not worth going. Any day could be a quiz day. Anyway, just show up every lecture. You have my assurance the material is interesting, and it's the best way to learn it, and it'll make your life easier. Anyway, so now let's go through the quiz. So this is an introduction of one of the types of analyses, or really 2 of them, that we're going to be doing in this class. These are going to be the ones that are the focus for the beginning of our class. This is asymptotic runtime analysis, is the term that we're going to use for this, and also correctness, which we'll talk about when we get there. So first up, I want to break down this bit of logical form that we have. So we say that f of x is O of g of x if and only if there exists some constant c and some value n naught. This is a notation that I'm stealing from a textbook, by the way, using the n naught. It just is another value, such that for every value greater than n naught, this function f of x is going to be less than or equal to c times g, or this should be n, sorry. I switched it to n here. F of n is less than or equal to g of n. Can anyone tell me in words what this means? I want to give it a shot. I'll give you a second to think. Maybe someone can do it. Yeah. So you're saying f of x is the upper bound of g of x. So it's actually the other way around. It's fair enough, I called it upper bound. So what this is saying is that g of x upper bounds. You can see that it's an upper bound. It's bigger. Yeah, so g of x is going to be bigger than f of x, but only under certain conditions. So let's look at two functions. Okay. Let's look at let's say f of x equals x. So let's just say f of x equals x. That's just a straight line, right? Now let's also consider g of x equals, so let's just say f of x equals x, and let's consider g of x equals x squared. What does that look like? That looks like this, maybe. Where what's this point right here, where they cross? 1. Because 1 squared equals 1. Cool? So we want to say, is g of x an upper bound on f of x, asymptotically. That's what we care about. We want to know, as n grows to infinity, is g of x bigger than f of x? That's another thing that this means. So what we can see is here is that there's some point, right, such that as we continue on to infinity, g of x is always bigger than f of x, right? So that's this point right here. So this right here would be my n0. It's saying past this point, g of x is always bigger than f of x. What about the c? Why do I have the c term here? Think about it for a second, what it would mean. I'm going to let everyone think for a second. Sure.
C is some kind of constant, so like in this example, no matter how low C would be, at some point, g of x would be greater than f of x.
Yeah, so I will say, so you're saying no matter what c we choose, we actually are just saying there exists some c. It doesn't need to be any c. So what this is saying is that sure, I might have some function where it's scaled down very heavily, like it's linearly scaled down, as long as these are only linearly different, right? If I can just scale this up or down, and then one becomes an upper bound to another, then we say that's an asymptotic upper bound. That's fine. So in general, in algorithms, when we're talking about asymptotic analysis, this is only going to happen when we care about asymptotic analysis, which is, we'll talk about in a second, extremely limited. When we do that, we don't care about constant factors. So let's keep this in mind. So we don't care about constant factors, we only care about other factors of this. And also, we only need there to be some point such that the other function is always bigger than it past that point. So that is asymptotic, means as I approach infinity. So as I approach infinity this direction, this function will be bigger than this function. That makes sense? There are other ways that we could phrase this, but basically it means that there is some point where they cross over and they never go back. Okay? And that's what it means to be an upper bound on something. So let's look at these questions now. So first up, the question is, here, let me erase this actually. This is a good image, by the way, to put in your notebook. This will come up multiple times. This is the type of analysis that we're going to focus on for probably a good third of the class. I mean, alongside other stuff, but this is going to matter quite a lot. And it'd be good to know this definition kind of by heart. You'll notice that I could write it out without any reference to my notes. That's because it's an important one. Okay, so first up, we have is 2n, I guess I'm writing it with that, is order n. Who said true? Raise your hands. Who said false? Okay, okay. Anyone want to give an argument? Yeah, go for it.
Considering this definition, if we set C to be example, then it's always true.
Yeah, so exactly. We could set it equal to, you also have to be careful with this. So we set c equal to 3, and then on this right-hand side we'll have 2n is less than or equal to 3n, right? Again, constant factor doesn't matter. So anytime we're going to see, you know, some function and then some constant multiple of that function, it'll always be true. That's just one thing that you can know now. But a little bit careful here, the n's, what about negative n's? So exactly, we need to set our n naught to 0 in that case. So just to be precise, generally we're not going to work on functions that have negative size. Generally this is going to be something like the length of an array or the number of nodes in a graph or something like that. So almost always this is going to be non-negative, but in this general definition, that's not necessarily the case. So be slightly careful, but it won't come up in practice for us. Okay, how about a slightly more difficult one? The second one was 3 to the n is order 2 to the n. Who said true? Okay. Who said false? All right. Anyone want to make an argument? Yeah. Yeah. Okay, so the basic argument is that there will always be a larger n, and this gap will always grow between them, no matter what constant factor you choose, which is a rough proof of this. You'll notice something here, something I want to point out to you. So it is in fact false. This isn't the case, which is something to keep track of. If it's not a linear factor, it's an exponential factor difference. Then it is no longer just written away by the c multiple. We only care about things that are beyond linear scaling. Beyond that, then we care about it. Beyond constant scaling, I mean constant scaling, not linear scaling. So one thing I want to point out about this is you may have noticed in the description here, it's substantially harder to prove that one of these is false than it is to prove that one of these is true. In the true case, all we need to say is, here's a value of c, here's a value of n naught, there you go. For this one, it gets a little bit more tricky. And this is a type of proof that not necessarily with asymptotic bounds, but this is something that we're going to need to get used to doing. So a lot of you, I think all of you have taken 250, so you're comfortable with some of these proofs, but we're going to be doing a lot of proofs, and we're going to be doing, in general, more difficult proofs than in 250. So reckon with that fact now, I suppose. I will give you plenty of help with them, but one other thing that will tend to happen with these is that they'll also require a little bit more creativity than the proofs for 250. A lot of the 250 proofs do require a lot of creative thinking and require a little bit of, like numerical knowledge or something like that. But these ones, some of them are particularly require an artist's touch to figure them out. So hopefully you all develop that, and that comes with time and practice. And throughout the class, you'll see lots of examples of this type of analysis. Okay, cool. Anyway, this, by the way, that was a rough outline of a correct proof for this. You can do this several ways. A proof by contradiction is a reasonable one. Basically, you can just set them equal to each other, and then show as n increases, eventually the sign will flip, no matter what c or n naught you choose. So just choose some arbitrary one, and then prove that at some point that sign is incorrect. That's a good way to do this disproof, if you wanted to write it as a formal proof. Okay. Lastly, I think I'll just read this one out loud because it's a little bit longer. If an algorithm is O of En, that means that it uses O of En floating point operations, it would be most accurate to say it is an exponential time algorithm. Who said true? Okay. And who said false? Anyone? Why did you say false? Okay, how about you? Any thoughts?
I just wasn't sure if exponential was reserved.
You need to speak up, sorry.
I wasn't sure if exponential was only in the number.
The base is e.
Yeah, the base was.
Yeah. So it isn't only used with that. It can be used with other things. The catch here. So this was the trickiest of the three questions. I'd say. It's sort of split between true and false, by the way. I can do that because it's just completion, by the way. So, but I'd say there's a good argument for false, actually. because all that we have, remember, is an upper bound. So if I had some function, like let's say x, or 2x, right? Is this true? Is this true? Thumbs up or thumbs down? Come on. Is that true? So this is in fact true because all we're looking at is an upper bound. So how you can read this big O notation, as we're going to call it, is that this is an upper bound. If this upper bounds this, and this will grow substantially faster, by the way, you can choose a C and an N naught to show that this is true, then it can be an upper bound. And you can have an enormous upper bound. You can have a really, really loose upper bound, as we'll call it, as there's a lot of room between your upper bound and the true function. But this function is clearly linear. So that is, it is just a linear function of x. So it would actually be most accurate, probably, to say that this function is linear. Now, if the only thing we know about the function is that it is O of ex, sure, it's a reasonable thing to say, and it is in fact always true. If something can run in exponential time, then it's an exponential time algorithm. But you know, in terms of the semantics, in terms of what we really care about, we care about how close we can get, how close of an upper bound we can get. This is going to be a key concept for all of us, is finding not only an upper bound, but finding a tight upper bound. We'll talk about this in the upcoming days. Anyway, so I would say that this is sort of a wash. I would say that it's reasonable to say false here, though. Yeah.
So when you say 2x,
Okay, I'll write it back. Yeah. 2x. So when I say this,
yeah, so like what's your argument behind that? Because like, are you saying that 2x is like less than like our x?
so precisely I'm using the definition of what this is. So if I were to plot these, again, 2 to the x would look something like that, let's say. E to the x would look something like this. It would become exponential very, very quickly. And what we find is that if I do some analysis on this function, there is in fact some point such that every point beyond this, E to the x is larger. Cool? So that's the basic argument of this. We'll find that there is sort of a hierarchy of functions in a lot of ways. So there is constant time functions, things that are not dependent on x. There's two. For example, if there's two operations independently of how big my input is, then I'd say it's constant time. If it's linearly dependent, then I'll say it's linear. If it's exponentially dependent, I'll say it's exponential. There's also logarithmic, there's polynomial, etc. We'll talk about the whole lot of them. There's going to be a lot of them to deal with. But there is sort of a hierarchy of it that is like constant, logarithmic, linear, polynomial, exponential is the rough ordering of them. There are many other things in between it. Like you might ask, what do I call something that's log n or something like that? We'll talk about stuff like that later. Anyway, there's a rough hierarchy. This is immensely larger than this, though. We'd say in terms of our hierarchy, it's way above it. Way above it. Good question?
Okay, so I just wanted to like reiterate. So if there's something such that beyond the right hand function, or such that beyond that function is larger, then you can generalize that statement.
Yes, that's exactly this definition. So again, to restate this definition, I suppose for like the fourth or fifth time here, just to really drill it in, because you're going to be using this definition in a lot of things coming forward. As long as there is some point such that from that point onward, they are at most linearly, they have a constant multiple apart from each other, then we say that this is an asymptotic upper bound of this. Okay? Or you can read it out, and you say, this is upper bounded by this asymptotically. You want to read it like that. Cool? Cool. All right. So next up, we have our very first algorithm. Not that you guys haven't written some algorithms before, but our first formal one. What we're going to do is we're going to take two lists. You can use, by the way, in general, I think this is coming up over here. When I say that I'm giving you lists or I'm giving you, a list of numbers, you can use whatever data structure you find to be very nice for that. Like if you want to, generally, unless we're operating in very, very low runtime, you can always convert between data types. So you can keep that in mind. If I want to make it into an array, if I want to make it into a dictionary or something like that, usually you can just do it. But if we're working on really, really low runtimes, I'll tell you when we're doing that. Then we have to be more careful of what data type we're using. Okay. So I'll have two lists. I gave you the example 1, 3, 5, and b equals 2, 4, 6. How can I take these two, combine them, and create a sorted array out of them? Anyone want to give a shout? I'll give you a second. You already answered a couple. Yeah. Okay. I know what you mean. I'm pretty sure, so I think I can explain it. Anyone else want to give an idea? Okay. So what we can do, this is the idea that is set here, is basically we can have, so there's other implementations of this, by the way. You can think of your own, how you would want to phrase it, but I'll use your implementation since you suggested it. I can have a pointer that tells me the index of each one of these lists. So I can have one they both start at 0. We'll call them like lowercase a and b. And then I'm just going to iterate until these lists are empty. And for each one of these, I'm going to compare the element at the 8th index of A with the bth index of B. A bit of a weird notation I chose, sure. And whichever is smaller, I'm going to append onto my output list. So I'm going to first compare these two, that one, compare them. One is smaller, I add one, and I remove it from this list. Or, as your implementation would have, you point your pointer one ahead. Okay? So you continue this, 2 versus 3. 2 is smaller, therefore I am going to move my pointer to the next element, so on and so forth. And there's the edge case, of course, if one of them is empty. How do I handle that? We just append the entire rest of the other array. So this is a fairly good way of doing this. Is it any more correct than if I just appended them together and ran a sorting algorithm on them? Is it any more correct than that? Thumbs up, thumbs down, I suppose. It is not any more correct, which is going to be a particular term, which means when I say an algorithm is correct, that means that it outputs what I say it's going to output, always. In this case, that is a combined sorted array. It would output 1, 2, 3, 4, 5, 6, and if I gave it any input, so when I say an algorithm is correct, that means if I give it any input, then it will work the way that I say it does. This is a little bit of a fuzzy definition because it is dependent on what I say it does, but generally it'll be very, very formally clear what the correct output is. Okay? In this case, a sorted array is very easy to verify what it means. Okay? So if we were to do it the other way, where I just concatenate them and run some sorting algorithm on them, I use Python sort or whatever, it is not, in fact, any more correct. That will work. I'm going to end up with a sorted array. Why wouldn't I do something like that? Yeah?
Because the sorting algorithm can then be a higher upper bound.
So, yes, it's going to be not just an upper bound, by the way, but yes. So we can look at this by counting. So I say, how many comparisons do I actually have to make here? Anyone? So number of comparisons. What is the exact number?
N log n?
No. Yeah?
-1.
It's going to be n minus 1. So this setup right here, I'm only going to compare each element one time. Right? Or I'm going to, for each element I compare, I'm going to append one thing onto here. That make sense? And it's n minus 1 here because he's assuming that they're the same length and one of them will be eventually empty. If I'm giving an exact number, it's actually going to be the minimum of the two of them. So slightly wrong, but also basically correct. So it would be the minimum of the length of the two of them. That is better than, as I'll tell you, the Python sorting algorithm will take n log n, as was said. It will take exactly n log n, actually. It will take that many comparisons to get here. So this is going to be an asymptotically faster algorithm. I'll give you the spoiler, it in fact will be a faster algorithm in practice too. It'll be fewer actual comparisons. Okay? Cool? Yeah?
Is n in this case the length of like A or the length of the whole?
So it'd be the length of both of them combined. Again, this is actually a very good point. N is going to be something we also need to be very careful with before defining it. For example, in the same algorithm, right, I'm saying, it's n comparisons, or n minus 1, or minimum of the length of the two of them comparisons, but how much runtime does that actually take? Well, it depends on the level of precision I have of these. It takes a different amount of time to compare floating point values than it does integer values, etc. So a lot of times we're going to end up having to we're going to have to consider not just like the more obvious thing, which is the length of these arrays, but we might also have to care about what data structure we do, how much runtime it would take for me to do a comparison between these two versus doing an addition of the two of them. So these sorts of things are how we get to very, very highly optimized algorithms, which we're not going to talk about for a while, but I want to bring it up because you asked. Yeah.
Okay, so basically you have a computer function for the first element.
Yes.
You remove the smallest element, add to the next list.
Yes. Yeah, exactly. So I'm just repeatedly comparing the first elements of the list and then removing the first elements and adding it to here, whichever is smaller. And so then this we said would be the number of comparisons would be minimum of the. This is going to be a standard notation for us, by the way. The length of A. That's going to be a standard notation. So we're going to use that in several different contexts. So might as well get used to it. It's going to be the minimum of the length of the two of these. It's going to be the number of comparisons. Okay. And I would also accept if you said n or n minus 1, all of those are reasonable answers too. But this is the technically correct answer. Yeah. Cool. I think that does give a little example also of where the sometimes the analysis of this is a little bit difficult. This is not as clear as this is. This is a very intuitive thing. Say it's n comparisons. You can work it out very easily mentally. But worrying about these edge cases is something that we're going to have to do later on in the course. Again, we're starting at the fundamentals. I understand that I'm jumping ahead a little bit. That's how I tend to lecture. But as long as you understand this basic algorithm and you understand that this is roughly n comparisons that we're doing, you're good. You're good at this point. Yeah.
I think it's going to be slightly more than the minimum. I think like if they're like two like interweaving cells, you're going to the amount of comparisons.
Oh yeah, it's gonna be yeah.
Are you saying it's going to be big over minimum?
Yeah, I will. But I was saying it's exactly. But that's a good point. I was wrong on that. Yeah. So it's going to be the max of them. It's going to be the max of them. Actually, I'm pretty sure. Because yeah. Whatever the case, it is definitely it's n minus 1 is upper bounded by that. I think it is slightly lower than that though. Yeah. Question? Okay. For the sake of everyone who may have not caught that exchange, don't worry about that. But do keep in mind that there is some sorts of analyses that we do like that in the future that are going to be a little bit tricky. Okay, yeah.
So you keep comparing the elements
Until one of them is empty. Yeah. There'll probably be a complicated expression for that instead of just the minimum of the two of them. Yeah. Okay. So the next big type of analysis, so all this has been, in a way, runtime analysis. I've been counting the number of floating point operations I do. I've been talking about asymptotics. The other big type of comparison or of analysis that we're going to start with is correctness. So this is the next term on here. I've already described what correctness means, but how would I go about proving it? I don't have any ideas of how I could prove that this algorithm works exactly how I say it does, or will always output the right thing. Yeah?
Induction. Induction.
Induction. So induction is a reasonable way to do this. This is something that you've all seen in 250. So I can induct on the basically the number of comparisons I've done, or on the length of the arrays, depending on how I want to set up my induction. And I can say basically every single one of these steps, I am adding the minimum available element, basically, to my array. So if I repeatedly do that, I will end up with a sorted array, just by the definition of sorted. It's one way we can do it. Any other ways we could do it? Yeah. Proof by contradiction. Tried and true. Contradiction is a very helpful one lots of times. Basically, you assume that this is not true. Assume that this algorithm is not correct, then prove that if it isn't correct, something else false has to be true. So just as a refresher from 250, in case it's been a little bit, if I say, statement A, and statement A implies false, then the only way for this whole statement to be true, so I do a series of implications saying that my assumption that my algorithm doesn't work eventually will lead through a series of implications to something that is necessarily false. That would be something like 1 equals 0, for example. Then what this means is that my assumption must be false. This is by the definition of an implication. You can maybe work it out yourself. But if I make some assumption and that leads to an erroneous conclusion, then I know that my assumption must have been false, and it's a good way to prove things that are sometimes tricky to prove. Just assume that they're false and show that they can't be false. Usually either proving that it can't be false or proving that it is true, one of the two will be easier than the other. So you can play around with them. There are certain situations I'd recommend certain ones, but the overarching message that I want to make here is that there will be lots of methods to prove what you're trying to prove in this class. There's not going to be, there are going to be outlines, there's going to be ways that you can structure that are going to be helpful, like doing induction, like doing contradiction, or things like this. But sometimes it will require you to be somewhat clever, to try out multiple things, and to come up with your method of proving and fit it to the right situation. Okay? So for this one, I think induction is a reasonable way to do it, although induction tends to be a little bit bulky sometimes. I lean towards contradiction personally, but that's a personal choice. Yes?
So is it correct for this algorithm, the number of comparisons is always at -1 comparisons?
So it will be more complicated than that. It depends what you define as n. If you define n to be the combination of the two of these, it will not always be exactly n minus 1, because sometimes if they're like, let's say A is entirely smaller than B, then I would just add this, and then I would just add that onto it. So the number of comparisons would only be the length of A, which would be the minimum of A and B, as if one is entirely smaller than the other. That was, sorry, doing it off the cuff is a little bit hard sometimes, but I was wrong about that one. But there is going to be some other complicated function. It'll probably be the number of interweavings between them. That is the number of times that one element of this is smaller than one element of this, plus the vice versa. It'll probably be something like that. If you'd like to work it out on your own, feel free. It's a good bit of practice. Yeah, but then for proving correctness on this, I would probably do a contradiction, or I would do an induction if I feel like it. There's some amount of, you should try to find an easy way to prove things, but in general, it's a good habit to prove things correct, rather than proving that they're not false. It's just more likely that you'll make a mistake in the other case. Yeah. Okay. Any other questions on this? Okay. So, little bit of a recap here. So, we are going to have, like I said, the front of this class is going to be heavily focused on different types of analysis. Those types of analysis, so far, we're gonna add more to this list, but so far, we have two major types of analysis that we care about. Right? Analyses, I don't know. We're going to care about, firstly, runtime analysis. And the way so far that we've seen that we can analyze with runtime is asymptotic upper bounds. So having some asymptotic upper bound on the number of floating point operations, for example, tells us roughly the order of magnitude of the amount of time that it takes to run. Is there any issues with this? Doing this type of analysis? A little spot check. I've said a few of them throughout. I'll wait on you again, sorry, but you'll get a chance if no one else. Yeah.
It's not necessarily the tightest.
Definitely not necessarily tight. That means that I could say that almost any algorithm is O of n factorial. Almost any one. And I'd be correct. For the most part, clearly it is not useful to just have n upper bound. I need to have a useful upper bound. We're gonna work on how to get tighter upper bounds in the future. We'll see that there is in fact a way to find a lower bound, and maybe you can figure out how we can get there from that. Yeah. Any other issues with it? Yeah.
It doesn't cover like any practical or average cases.
So exactly. So this is a worst case analysis also. So one thing that it may have not been entirely clear, but if I say that my algorithm always will run in under this amount of time, Perhaps there's cases that are much slower than others. We just talked about this actually with the sorting the algorithm. Some of the cases are very easy. Some of them are very difficult. If they're fully interweaved, then it would take n-1. If they're fully separated, it would be the minimum of the two, which is less than n/2, right? So in practice, it's very